was.
Good morning. I would like to continue the problem that I started last lecture to compute the trajectory of a falling object or a sphere. We write Newton's law to get an equation for the speed and then write the definition of speed, which is the derivative of the position with respect to time. So the first thing I want to address is how to select a time step for using in the Euler method. How do you select that time step? So one insight I want to give is this is usually specific to a problem. Can't just universally say I'll use a time step of 0.01, which doesn't mean anything. If you have a problem with real units, the first thing we can think about is what is the total time that this event takes place? That is, the free fall takes some time. So we would write, for example, you think about the forces, the weight here is a constant, whereas the drag force increases with time or increases with velocity. So at some point they'll intersect, and this velocity alpha vt squared equal to mg is called the terminal velocity. It's like the steady velocity or the steady speed with which the object will keep falling after a while when it has attained the balance between gravity and drag force. So Vt here would be mg divided by alpha, okay? Sorry, mg divided g equals alpha Vt squared equal to g. So this would be g over alpha square root. And just to make the numbers easy, I kept it as 9 meter per second squared divided by 1. I think I have to write this as the correct unit of alpha. dV dt is meter per second squared equal to alpha meter squared per second squared. So this would be per meter. So that is correct, per meter. So this will be, this will be per meter. So this would be 3 meter per second. 3 meter per second is the terminal speed. So the average or nominal falling time would be the height divided by the terminal speed, which would be, I think last time I said this is 100 meters. Just to again keep it simple, we'll keep it as 30 meters. So that your T fall comes out to be 10 seconds. So it's like telling you, you need to simulate an event which is expected to last about 10 seconds. It will be a little bit less or more. So now how would you select a time step? So you would generally go as time step is some fraction, we'll call it gamma, times a characteristic time. Characteristic time for that process. This process happens to be the object falling down over a period of 10 seconds. So well, let's say we choose gamma equal to 0.1 or dt equals 0.1 times 10 seconds or 1 second. So we are going to simulate this free fall with a time step of 1 second. Okay. Are you guys with me so far? Santiago, Kylie, okay. So we have two equations. I'll call this first equation. I'll rewrite it as dv over dt equal to f of t comma s comma v or f1 of, and ds over dt is f2 of t comma s comma v. Just to keep it easier to write the Euler method. Are we together? Good. Yes.
So it's gonna take 10 seconds to fall completely.
That is a nominal calculation. The for throughout its fall, the velocity isn't exactly 3 meters per second. It's like it takes a while to attain this terminal speed.
Okay.
So until then it is accelerating. So it is slower than 3 meters per second. After that, we plot the velocity. Here is 0, here is 3 meters per second. It attains it something like this.
So the gamma for 0.1.
Yeah. That is a choice. We make that choice. Sometimes if we want to make it very fine, you can choose 0.01 or 0.001. You can make it as fine as you want.
So like in this case, you're gonna be 10 iterations, right?
We are going to do, we are saying 10 seconds. That doesn't mean we are just going to simulate up to 10 seconds. We'll simulate up to the point the ball hits the floor, up to when this S becomes 0 or less than 0. S starts at 30 meters and it has to go to 0 for you to say it has struck the floor. Okay, can we proceed? Yeah? Are you okay? All right. So I'm going to erase this side. We have chosen a time step. And now I want to write the numerical method. Now this part here, where we write the numerical method, today or this moment we are talking about Euler method. Half an hour from now we'll be talking about. I'm recording it, so don't nobody's notes.
Thank you.
Took it?
Yes, sir.
Okay, good. So this moment we are talking about Euler method. There are two other methods we'll study. So this part of what I'm going to say can be swapped. You can swap it with another method. Okay. So we'll write to write the velocity at the next time step is velocity at the current time step plus the delta t multiplied by the function f1 of t comma s comma v. And the position at the next time step is equal to position at the current step multiplied by delta t times f2 of t comma s comma v. So we start with, we will make an Excel sheet for this. We start with time. We write what is the velocity at that time, the position at that time, and then we keep iterating. So we start with 0, time 0. What is the velocity given to be 0 because we are just gently dropping the ball without giving it any initial velocity. So this is 0. And its initial height is h, which I have taken as 30 meters. So this is 30. So this has units of meter per second, this has units of meters, this has units of second. With me so far? Good. I know we missed a couple of minutes. You're okay back there? Okay. So what's the next step? Our time step is 1 second. So the next time we'll simulate is 1.0. So I'll do a calculation here. So V at time 1 second equal to V at time 0 plus delta t, which is also 1 second, times F1. What is my function F1? That is G minus alpha V squared. G, which I have taken to be 9 meter per second squared, minus alpha, which is 1 per meter, times V squared. What is my V squared? 0 squared. 0 meter per second squared. Obviously, this is 0 and this is 9 minus 1, 9 minus 0. So this would be 9 meter per second. Which makes sense, right? That's what acceleration is, which is how much speed you pick up in 1 unit of time. So in 1 second, you would pick up 9 meter per second. So that makes sense. Okay. And then the position after the first second is s at t equal to 1 is s of 0. What is s of 0? 30 meters plus delta t being 1 second times what is my v? My current velocity. Whatever my current velocity is, 0 meter per second. So s is, s is still 30 meters. I think I made one mistake here. Position has to be, position is s equals 0 here and s equals h here. So position has to decrease with time. I'm getting a sign wrong. P minus. Right? If I say my s is pointed upwards is positive, and my velocity is defined as downward positive, there should be a negative sign. Yeah.
Is it the gravity?
Gravity. So if I say gravity is -9, that won't solve the problem. I mean, it is intuitive to think, well, speed increases as you fall and height decreases as you fall. So let's just keep this here, okay? Or we could do this as s equal to 0 and this is s equal to h. When you reach h of 30 meters, okay? So in that case, initial condition will be 0. So this will be 0 meters plus 1 second times 0 meter per second, which is simply 0 meters. So you can then repeat the calculation again for v equals 2 seconds or velocity at 2 seconds, which is the velocity at 1 second, 9 meter per second, plus 1 second times 9 meter per second squared minus 1 per meter and 9 meter per second squared. Something is not adding up here. Square. So if v is 9 meters per second, this becomes 81. That is 9 minus 81. That's like the ball suddenly reversing upwards. Maybe we should use a smaller time step. Okay, let's continue this on Excel. Okay, maybe we'll use a smaller time step and repeat the calculation. Up to here it's fine. Let's continue this on Excel. Okay. So one thing I did yesterday is to find out all the examples I did in previous terms and put them in the same file and post that. So when you're practicing, you should be getting a lot of examples to find here. Okay. So let's see here. We were here. Okay. So I want to compute the speed or time and then the speed v of t and then the distance s of t. All right. Time 0, speed is 0 and position is 30 meters. This has units of second, meter per second, and then meters. So we'll use a dt, which is 1 second. We'll see if that actually we made any mistake, or otherwise we'll go for a smaller time step. Okay. So this will be the previous value plus dt. That's the first thing you got to enter. Previous value plus dt. Whatever dt is. Could be 1 second or 0.1 second or in. I'll post this file also. Okay. So how do we calculate velocity? Velocity is previous value plus dt times the function f1. Maybe I'll write it. So my equation is dv dt equal to g minus alpha times v squared. That is my function, where g is equal to 9 and alpha equal to 1. G equal to 9 meter per second squared and alpha equal to 1 per meter. So we'll write the next velocity. So if I say this is current, this is my next. This will be current plus dt times. I have to execute this function in g9 meter per second squared and then alpha 1 per meter. So this is current plus dt times g minus alpha times v squared. I'll give you a minute to implement the formula. You good so far? Oh, that's okay. You can go sit there.
Yeah, I'm probably gonna do that.
Up to here, is everybody following? Right? We're calculating the speed. Done. Something. Tell me.
Explain how you're learning it, please.
Yeah, so let me see if I can annotate here. So I'm sure this question is with others also. So let me explain this. Please listen. Right. So what is the Euler method? It is to write dy dt equal to a function which is dependent on time and y. So it's like writing y at the next time step at t plus delta t equal to y at this time plus delta t multiplied by f of t comma y. You're okay with this? So I'm just applying that for our equation, which happens to be this one, dv dt equal to g minus alpha v squared. So if I want to write the velocity or speed at the next time step, I would say it is equal to whatever the current value is plus dt delta t multiplied by the function, which happens to be g minus alpha v squared. So if I show you my formula here, you see my formula. Made it bigger. This cell, I take the previous cell plus dt multiplied by g, which is a constant, minus alpha constant times b squared, 0 squared. Are you able to get now? Okay. So then what is S? What is the equation for S? ds over dt equal to V. So S will be the current value plus dt times whatever V is, which I put 0 here. I think I should have ds dt equal to minus V. That will make sense. So this will be plus d plus minus d3 times minus d3. This is where we ran into problem. What is our next time step? That will be 1 plus 1 second or 2 seconds. And if I drag my formulas again, that's the power of Excel, right? To just automate it quickly. I'm getting minus 63 and 21. That makes no sense. How can the ball suddenly flip its velocity and start going upwards? That can't happen. So we'll try reducing our time step and see if that makes a difference. Oops. All right. So let's use a time step of 0.1 seconds. Okay. I'm using a very small time step. The reason we got that answer, that absurd value, I'll come to it. But if I use a time step of 0.1, it says my speed is increasing from 0 to 0.9 to 1.72, and my height is decreasing from 30 to 29.9 and so on. So what you should do next is to just, if you have this automated, like set up with the dollar signs, you just have to drag this and simulate later times. Okay, I'll wait. Tell me if you are able to get values for the speed and distance all the way to 0. That is all the way when the height becomes 0, which is when the ball strikes the floor. I'll wait. Tell me if each of you is able to get this. You got the first two rows right. then all you have to do is drag it down until the value of S flips from positive to negative. Okay, what value of time? You're still using time step of 1 second. I have switched to 0.1 seconds. The reason 1 second isn't working is because this Euler method is such a very poor approximation of the derivative that it's just accumulating the errors very quickly. So you want to use the time step that is fine enough. So let's say we use 0.1 seconds. Are you able to get the time 0.1 and 0.2? If you're able to get that, then you are mostly done. Anna? Yes, you are able to drag the formula. Okay, Cole, okay. Yeah,
Then you just highlight it, right?
the corner. Yeah, pull that corner. Drag also the time. Time is critical. You're making some mistake in your formula. Check if you're putting the dollar signs. If you don't put the dollar signs, it won't count. Dollar signs, if you miss those, it won't happen. Okay, so you have the speed and the velocity. Okay, so let's plot it. I'm going to make a plot of the speed versus time. Okay, I'm going to make a plot of speed versus time. So here is my graph. What do you see here? What is the behavior? It's very thin. Maybe I'll make it a little bit bigger. So here is the speed of the sphere as it falls. Here is time on the x-axis. What are you seeing here? You're seeing a plateau, and what do you infer from it? What do we infer from this? This is the speed. Initially, it rapidly increases, then the increase slows down, and it hits the terminal speed and then stays there. Sorry, it's in free fall. It's always in free fall. Over here, it's accelerating. At this point, it's not accelerating. If speed is constant, what does it mean for the acceleration? 0. It's not accelerating, right? And what about if I plot the position? The position as a function of time. So here is both the speed and position. Of course, the speed stabilizes and reaches a plateau, whereas the position almost. So what is the implication? Look up here, please. There is this period during which the speed is changing, and then the speed is constant. So what can you say about the slope of this curve, slope of the orange curve? It should be constant because it corresponds to constant speed, right? So this is what we mean by saying the trajectory, which is the position and the speed of the object as a function of time. And how we got that is by solving a set of two ODEs, one for speed and one for the distance, which are coupled to each other. Okay. All right. So we saw this very simple method, right? The next step we want to do is how do we learn more accurate techniques? Because this 0.1 seconds is such a small time step compared to 10 seconds. Can we get the same level of accuracy but with a larger time step? So that we do by using different variations of the approach, which I'm going to talk about. Okay. At this point, any question in this problem? I wanted to show you this. Here is the quiz that I've been working on, or the mock quiz. The quiz. Yeah, quiz 6. Yeah, quiz 6. I have it open here. So quiz 6, what I've been thinking is we'll have just download it. All right. So look up, please. Here is quiz 6 that I've been working on this morning. So calculate the settling time of a particle which is of diameter 10 micrometers falling due to gravity. Gravity acts on the not on the bird, but we'll say aerosol particles. Air resistance acts along the y component, along the y direction proportional to the velocity component. Okay, so I want you to be able to write a set of equations which describe the settling time. What do you mean by settling time? You drop it from a height, it takes a while for the particle to come down and reach the bottom. That period of time is the settling time. How do you identify it? It's the time for which the particle's position goes from being positive, 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 touches the floor where it is 0, and if it starts to overshoot, that becomes negative. So it's when the sign changes from positive to negative. Okay, so this is one of the problems I've been thinking. The other problem being, solve a second order ODE using Euler method and then plot the solution as well as its derivative as a function of time. How do you solve this problem? That is, Euler method, what we learned so far, has been shown to work only for a first order ODE, but this is a second order ODE. What do you do? Say it again.
Or substitution,
What substitution? What will you substitute?
the higher orders are.
So you want to call dy by dt equal to say z, which will make d squared y over dt squared equal to dz over dt. Reduce the order by doing a substitution. Okay. So let me fix that here. There's a problem, small mistake. So let's do this problem now. Okay. I want to do this just with pencil and paper first, and then we'll put it on the computer. Okay. So copy this and then we'll solve it by hand first. Is everybody okay with the other problem, the problem of free fall and trying to simulate the trajectory, the height and the speed? Okay. Okay. Once you have written down, we'll start solving. So since your quiz and your exam, that is the take-home final, is going to be using Excel at home, I'll ask you to do plotting and stuff within Excel. But for exam 2, which is going to be in class 60 minutes, it will be just pencil and paper, so just hand calculations. Okay. You okay? Tired? All right. So if you have written this down, switched off. Suppose this is your exam problem by hand. Let's go through the steps. Okay. So we'll have a full solved example to go with. So we we have d squared y over dt squared plus 4 dy dt plus 3y equal to, what was it, sine 2. Okay, step 1, substitute higher order derivatives with expressions such as, let's say, z equal to, or dy by dt equal to z, which implies the first equation becomes dz over dt equal to sine 2t minus 3y minus 4z. So we have immediately reduced the second order ODE into two first order ODEs. Okay, so I'll call this F1 of t comma y comma z, and this is F2 of t comma y comma z. With initial conditions, we were told y of 0 equal to 1 and y dash of 0, which is nothing but z of 0, equal to 0.5. What was the suggested time step? 0.01. Okay. Okay. Thank you. 0.01. 0.01. All right. The suggested time step dt equal to 0.01. So we want to write y at y at t plus delta t equal to y at t plus delta t multiplied by f1 of t comma y comma z, and you also have to simultaneously calculate the z value or update the z value. Z at t plus delta t equal to z of t plus delta t multiplied by f2 of t comma y comma z. This template will always be the same for every problem. Your task is set up the ODEs and carefully identify which is F1 and which is F2. So you are given y of 0 and z of 0, right? Let's start with what is y of 0.01. That will be y of 0 plus 0.01 times what is f1 of 0, which is z of 0, which is only 0.5. So I'll write 0.1 times z of 0, or this is 1 plus 0.01 times 0.5, or this is 1.005. And what is z of 0.01? That is z of 0 plus 0.01 times, this is f2, sine 2t, t being 0. So this is sine of 2 times 0 minus 3y, 3 times y of 0 minus 3 times y of 0 minus 4 times z of 0. We know z of 0 given as 0.5. So 0.5 plus 0.01, this is 0, minus 3 times 1 or minus 3, minus 4 times 0.5, which is minus 2. So this is 0.5 minus 0.05 or 0.45. When you do this for exam 2 as a handwritten work, this step, doing the substitution, this step, writing down the algorithm, and then this step, calculating the first value, that is from the initial condition onwards, the very next value, that is the most critical. If you get this right, the rest of it you can be trusted to do. It's just repeating the same thing. So if you make a mistake here, suppose I ask you, what is the value of y at 0.03 seconds? If you make a mistake here, that mistake will just carry over and carry over. So this is a very important step, okay? So this 1, 2, 3, and then after 4, that is from step 4 onwards, it is just to do successive times, which we may typically do with Excel, that is in a quiz or a take home, or I might ask you to do 2 or 3 values. I won't ask you by asking you to do 20 values. So there are 2 types of problems you need to be able to do. One is second or higher order ODEs. That is, if you have an equation, suppose you have d cube y over dt cube plus 4d squared y over dt squared plus 3 dy dt minus y equal to some f of some equal to 0, let's say. So the substitutions you need to make are set, say for example, dy by dt equal to z or z1, and then dz or d squared y over dt squared equal to dz1 over dt equal to z2, and then d cube y over dt cube equal to dz2 over dt equal to z3. So this first equation actually something we need this substitution now. First equation becomes dz2 over dt plus 4 confused d cube over dt cube equal to dz2 over dt. So the first equation becomes dz2 over dt plus 4 times z2 plus 3 times z1 minus y equal to 0. So you have 1, 2, 3 equations to solve using the same technique. So this is one type of problem, higher order ODEs, which reduces to a system of equations. How many equations? Number of equations equal to order of the differential equation. The other problem I would ask is simultaneous ODEs. Which are also really the same thing like a trajectory calculation. Like a falling particle, its height and speed and so on. If you are able to handle this trajectory calculation, in principle, you would be able to do any simultaneous equation later. Like for example, in your control systems or spring block systems, structural analysis, you get a lot of time dependent simultaneous equations. They are all of the same template. So we'll just see one of those. So for your quiz 6, there will be two problems. Problem 1 is going to be a trajectory calculation. And problem 2 is going to be like a second order ODE. Telling you right now. Only thing you need to be guessing is what method. Is it going to be Euler method or is it going to be the other methods I'll go over now. With me so far? Okay. A lot of instructors frown upon students eating lunch in their class. I just get hungry. So you're just reminding me of lunch. Okay, so I've been using Euler method to illustrate all these ideas because it's the simplest method there is. But now we are going to amp up the complexity in the algorithm, which is going to be in the form of section 25.3 Runge-Kutta methods. It's a very classic set of techniques in numerical methods. So whatever we saw so far, section 25.1 is Euler method, and 25.3 we are going to see what are called Runge-Kutta methods. And within that we are going to see two variants, second order and fourth order Runge-Kutta methods. So for your both quiz and exam and final, these three are the topics that we are going to cover. Plus, we are going to solve, or plus using these methods, we'll solve simultaneous ODEs and higher order ODEs. So three methods, two types of equations. That's it. All right, what is this RK method? So RK2, Runge-Kutta second order method. Now, if you recall, when we did Euler method, do you recall what that method is about? If you have a time point, we'll call it Ti. And if you have a time step, we'll call this Ti plus 1, which is equal to Ti plus delta T. And we say at this point, dy dt equal to f of t comma y, or we write, if this is yi, and the next point is yi plus 1, we write that this is a constant slope equal to di over dt at I, which is equal to f of ti comma yi. So we write yi plus 1 equal to yi plus slope times delta t. This is Euler method. The simplest method, just by saying over this delta t, we'll assume a constant slope and get the next value. Okay. So we write this yi plus 1 equal to yi plus delta t multiplied by f of ti comma y. The RK method isn't very different. It is just like a sort of a better approximation, like in the sense, drop your pencil when you're done writing this, drop your pencil and listen. This is sort of crucial. The function you are calculating, which is y, okay, you are always trying to calculate y of t, which is the solution. The true form of that function could be something like this. It could be something like this. The yi plus 1 that you calculate is not necessarily the true value of the function. It is an approximation of the truth. So the function could have a slope which could be steeper or it could be slower than the straight line that you think it is. So at this point, I'll wait for you. I want you to listen. At this point, the slope is given by the value of the function f. Okay. It is just that point. If you travel a few steps further to the right, there is no guarantee that this slope will still hold. In fact, it won't hold. By how much it will differ is the question. Okay. So if you're taking a time step delta t, whatever that time step is, if this function is a rapidly changing function, even in that small time, the slope can be rapidly changing. That is the implication. So instead of covering the entire time step and saying at the next time point, it is just the slope multiplied by delta t, RK method, what it does is it just divides. So here is ti, here is ti plus 1. What RK method does is it takes this entire interval delta t and divides it into two halves. So this is ti plus delta t over 2, and then this is ti plus delta t. So it splits that interval into two segments. Okay. So then what you do is you calculate an intermediate value. Based on this triangle. So this is ti. This is ti plus delta t over 2, and this is yi, and this is y intermediate. Okay. And then what it does is using this ti by 2 and y intermediate, it again makes another approximation for the second half and gets you one more value at the next point. Finally, what it does is to take an average of the second calculation and the first calculation and get you something that is supposedly more closer to reality. It's like you are taking this delta t segment, you are chopping it into two segments, and then using two applications of Euler method to come up with a better approximation for the yi plus 1. That is RK method. Chop the segment into two steps, repeatedly apply Euler method and get the answer. Okay, why do you have to stop at 2? Why can't you segment this in 3 or 4 segments? Can you conceivably think of the same process but with 3 or 4 segments? Can you or can you not? It will just be more complicated, more lengthy formula, but you can, right?
Especially if you're using software.
That complications can be handled, but in principle, can you think of this segment being chopped into ti plus delta t over 3 and ti plus 2/3 delta t? Can you think of that? Or think of ti plus 1/4, 1/2, 3/4, and then that is RK3 and RK4. So it's not necessarily more complicated in concepts. It's just a better way of chopping up this interval and thinking of more finite or more number of fine approximations of the slope to get you a better average in the end. Okay. So you can go through the derivation of how RK4 or RK2 comes about, but I've tried to explain that to you intuitively, like from the gut, instead of trying to do this with Taylor series and math. Okay. So instead of presenting you like a mathematical derivation, I'm going to present you the two equations you're going to use for RK2 and RK4 So along with Euler, these three are the ones that you need to be able to use in your exam or quiz or whatever. All right. So let's write out RK2 method. Okay, it is given in page page. Yeah, page 732, equation. I got it. Equation 25.38. So RK2 method, page 732, equation 25.38. If I were you, I would put this on my cheat sheet for the exam too. Okay. So it goes like this. Actually, there are two variants of the second order method. We'll use the variant that is presented in equation 25.36. That's the one I talked about. 25.36. Okay. So yi plus 1 equal to yi plus delta t multiplied by k1 divided by 2 plus k2 divided by 2. What is k1? K1 is the value of the function at ti and yi, and k2 is the value of the function at ti plus delta t over 2 and yi, sorry, at delta t and yi plus k1 multiplied by delta. Oh, wait. No, we'll just stick to this. So this is the variant you're going to stick to. And one thing you should remember is there are many ways to dividing the interval delta t. That is, I said you can do this 50-50, half and half. You could do this 1/3 and 2/3, or you could do this 40%, 60%. Each of those will give you a new variant, but we'll just stick to the variant that is half and half because it's easier to think of. So this is one of the methods, RK2, and then we'll also use RK4, which is obviously a more complicated formula, which is given in page 735, equation 25.40. Page 735, equation 25.40. And because we are doing this listing thing, I'll also write Euler's method is given in page 710, equation 25.2. Euler method is page 710, equation 25.2. So the three equations are what you need to know. So RK4 method is yi plus 1 equal to yi plus delta t over 6 times K1 plus 2K2 plus 2K3 plus K4, where K1 is f of Ti, Yi, K2 is f of Ti plus delta T over 2 Yi plus half K1 delta T, and K3 is f of Ti plus delta T over 2 and Yi plus half K2 times delta T, and K4 is f of Ti plus delta T Yi plus K3 times delta T. So this on the right side, this panel here is the summary of this unit of this differential equations or numerical methods for differential equations. Okay, let's do some examples. So remember we did this second order problem with Euler method, and then we said we'll continue on Excel, right? So we'll revisit that. And we are going to do the same problem using two methods, both using Euler method and the RK2 method, and see what are the differences. For using delta T equal to, what was the delta T I said before? 0.01. 0.01. Okay. Using a delta T of 0.01, obtain y of t and the derivative of y with respect to time, y dot of t for t equals 0 to 1. Of course, 0 to 1 means I'm implying we'll do it on Excel, okay, not everything by hand. So if you are applying the Euler method, okay, actually before Euler method, you will write dy by dt, substitute dy by dt equal to z, which implies dz over dt equal to sine 2t minus 3y minus 4z. We'll call this f1 of t comma y comma z and f2 of t comma y comma z. Initial conditions for each: z of 0 equal to 0.5, y of 0 equal to 1. Let's start here, and then we are going to switch to Excel now. Okay. With me so far? We are now going to switch and do this problem with two methods. Okay, maybe even third method. Can I bring down the screen? Yeah. Okay, so this is one of the mock problems on the quiz. Okay, so here is my equation. Everything is set up. So I'm going to write first column. I'm going to write time t, and then I have y of t, and then z of t. What is z of t? It's nothing but dy dt. Okay, at time 0, what is y? 1. What is z? 0.5. So this is first we are going to do only the Euler method. We are using a dt of 0.01, and this is Euler method. So I'll calculate dt time. This is current plus dt times. What is the function for what is the function that we use for? Let me write it here. So f1 of t comma y comma z is what? What did you write in your notebook? What is f1? That's just z, right? So I'll type that is just equal to z. And what is f2 of t comma y comma z? That is sine 2t, sine 2 times t minus 4 times z minus 3 times y. That is my f2, f1, f2. So if you want, I'll write it here, f1 equal to z, f2 equals sine 2t minus 3y minus 4z. Yeah, okay. Is this fine? Can we proceed? Yeah. So what is y of t? I'll write it in the side here for reference. Y of t plus delta t equals y of t plus delta t times f1, and then z, the same template, z of t plus delta t is z of t plus dt times f2. If you understood this step, you are pretty much good to go. So I'm going to update y, which is to add the current value plus dt, put the dollar sign times f1, and then z, which is the current value plus dt, put the dollar sign times f2. And then I'm done actually. You get these two numbers with the dollar sign, you're done. After that, it's just dragging across. Tell me if you are able to get these two numbers. Okay. Let me know how are you able to get or you're able to get this. Yeah.
You show, the minus.
Yeah.
Please.
So if you see here, y of t is the current value. If you want, I can add a annotation here saying this is current, this is next. So it's the current value plus dt multiplied by f1 as I've written here. Same thing goes for c, current value plus dt times f2. When I first learned this type of techniques, and they told me you can solve nonlinear equations with this, there is no restriction, you can solve any kind of ODE. I felt so powerful, like, wow, I can solve everything now. I don't have to have no math, I can just put it in an Excel sheet and I'll have the solution. It felt powerful. Okay. Are you able to get these two numbers for y and z? If you have, please tell me so I can move forward. Okay, quiet. Yes. So then next step is just for you to look at the solution that you got, plot it, just see how it looks. Okay, I'll plot this as a secondary axis so that one of them is to the right and one of them is to the left. So you see here the orange is the z and the blue is the y. So the solution that you are asked for is to calculate y and its derivative, which is these two curves. So if you are doing kinetics, especially drug absorption kinetics, you would inject something in the blood, take blood samples every few hours, and then measure how much that substance is still in the blood, right? Could be for coffee, alcohol, or any drugs. So this is basically that, calculating how that substance decays in the blood or something. So we did this with a very simple method, the Euler method. Now I want you to do the same using the RK2 method first. RK4 will hopefully get to it by next lecture. RK2. Okay, write down the. Is everybody here? Can we go back and write down RK2 and then start over? Yeah. Okay. All right. So then this part remains common. Okay. Only thing you need to understand here is when you're going to calculate the value at the next time point, that is next, as a function of current. Here for Euler, you did this. For Euler, you have yi plus 1 equal to yi plus delta t times f of ti comma yi. Pay attention, please. Here you just do one calculation of the function to get the next value or the value of y at the next time step. Here you have to do two calculations, k1 and k2. That is, you have to calculate the value of f twice, one at the initial point and then at the end point or midpoint. Okay. Other than that, in terms of complexity, so here, for example, you write y at t plus delta t equal to y of t plus 1/2. We'll call this K1y plus K2y. And then z at t plus delta t equal to y of t plus 1 half K1z plus K2z. What is K1y? That is equal to F1 of Ti, comma Ti, comma Yi, comma Zi, and K2y is F1 of Ti plus delta T and Yi plus K1y delta T and Zi plus K1z times delta T. That's the only change here. If this is not easy to read, I'll rewrite it. I'll rewrite it more clearly or more. So K1, K2y is F1 of Ti plus delta T, Yi plus half K1y times delta T, comma Zi plus half K1z times delta T. You may be wondering what is K1z and K2z, which we haven't defined yet. I'll write here what is K1, K1z and K2z. K1z is F2 evaluated at Ti, Yi, and Zi. K2z is F2 evaluated at Ti plus delta T and Yi evaluated at Yi plus half K1y times delta T and Zi plus half K1z times delta T. You notice these three arguments and these three arguments are really the same. They will always be the same. It's just that they are fed into two different functions. Are we good? Can I bring down the screen and we'll do this on the computer? Okay. So for your quiz, I just asked Euler and RK2. For the exam 2, we'll test you on RK4. Okay, because whatever we do until today is what the quiz will be. We'll have one more lecture on Tuesday to go over RK4. So this is our solution which we did with Euler. Okay. So now we'll just go below here and we'll start another solution where we say copy some of this. Okay. So this remains the same, right? Your F1 and F2 that remains the same. Okay. So then over here for reference, let's write down what is y of t and z of t. Y of t plus dt equals y of t plus dt divided by 2 k1y plus k2y. Z of t plus delta t equals z of t plus dt over 2 times k2y, I'm sorry, k1z plus k2z. Remember, what is the difference? We have to execute this function f1 and f2 twice. That is the main difference. Okay. So we'll keep these two columns. We'll keep these two columns. Okay. So this is like saying what is f1 and what is f2. We'll keep that. K1y. What is K1y? This is the value of the function at evaluated at t, or t comma y comma z. This is the value of the function evaluated at t comma y comma z. K2y is the value of the function evaluated at t plus dt y plus k1 times dt y plus half k1 times dt y plus 1 by 2 k1 y times dt and z plus 1 by 2 k1 z times dt. Okay. Maybe we should do this after here. Okay. So what is K1z? K1z is the function f1. K1 or K1z is the function f2 evaluated at t, y, and z. Okay. And then K2z is going to be the function evaluated at t plus dt. Same arguments. So I can just copy this. I just have to write K2z is f2. I know it's a lot to type, but are you following so far? Yeah. Because we are almost out of time, I'm just going to do 2 rows and hope that you can take it from there. Okay. All right. So you can see this argument here. It's sort of it's sort of what you need. And as a tip to keep it clutter free, I would suggest that you create 3 columns that are t plus delta t. So I'm going to say create t plus delta t, k1, sorry, y plus k1y or y plus half times k1y times dt, and then z plus half times k1z times dt. See, this is easy. This is just plugging in whatever time value is directly. Whereas this is like a half point, which you would calculate, as what is t plus dt? That is the current value of time plus whatever dt is. Put the dollar sign. Okay. And what is this? Y plus half k1y dt. What is y? Y is right here plus half times k1 is right here times dt. Don't forget to put the dollar sign. And then what is this? Z, which is right here, plus half k1z, which is here, times dt. Put the dollar sign. So the reason I create these three values is, I'm sure you would understand. This function f1 has three arguments. This function f2 has three arguments. So I keep this nice and organized. So what is f1? You know f1. F1 is simply z. Whatever z is, that is equal to f1. And k2, f2 is sine 2t. F2 is sine of 2 times whatever time is minus 3 times y minus 4 times z. Okay. So you have this. Almost done. Bear with me for just 1 minute. Okay. So almost this. Then you come here. What is y of t? What is your golden formula? It is like writing the current value plus dt times or dt divided by 2. I'm sorry, dt divided multiplied by k1y. Okay, here is k1y plus k2y, the whole thing divided by 2. And then what is z? Current value plus dt multiplied by k1z, which is here, plus k2z, which is over here, divided by 2. That's it. Now you have your y and z at the next time step. If you have done the previous step correctly, the rest of it is just a matter of dragging this down. Is correct? Did I make any mistake in my haste? Dollar sign. I've been telling you all day, dollar sign. Freeze it. There we go. Okay, so the solution is changing. So you can go home and check this. I will update this file, also add a second quiz problem and post this by tomorrow morning. Okay, so you have until Tuesday to do the quiz. One thing I do tell you is the mark and the actual quiz will be very similar. I want you to learn the technique on the mark and apply it on the real quiz. Okay, by Tuesday. Tuesday 11:20 is the deadline. Okay, thank you and sorry for running over.